Welcome to Talk Tensors. It is Tuesday, February 24th, 2026. I hope your gradients are flowing and your learning rates are scheduled. I'm your host, and today we're cracking open the archives for a professional machine learning deep dive into the papers that really built the modern AI landscape.
Yeah, it is great to be here. And, looking at the calendar, it's actually amazing to think about how much has changed in the last decade or so, but also, how much has stayed exactly the same when we're talking about the fundamental principles of stochastic gradient descent and optimization.
Oh, completely. And I think to prove that point, we are going back to a time that feels like absolute ancient history in AI years.
Oh yeah, late 2017.
Late 2017, early 2018. But this was genuinely the turning point for visual synthesis. We are diving into the paper, Progressive Growing of GANs for Improved Quality, Stability, and Variation.
A truly monumental paper. This one comes out of Nvidia, authored by Tero Karras, Timo Aila, Samuli Laine, and Jaakko Lehtinen.
Right. And if I were to just, summarize this paper in a single sentence for you listening, it would be this. This paper fundamentally solved the high-resolution bottleneck in generative adversarial networks, or GANs.
Not by creating a massively complex new architecture.
Exactly. But by treating training as a curriculum. They essentially figured out that you have to start small if you want to grow big.
That is the thesis, yeah.
Exactly. Yeah.
But the devil, and really the brilliance of this, is in the engineering. This paper is the exact reason we went from generating these blurry, postage stamp-sized nightmares where you literally couldn't tell a dog from a muffin.
Right, the classic 32 by 32 smear.
To generating these 1024 by 1024 megapixel celebrity faces that looked startlingly, almost uncomfortably real.
I want to start with the hook here, actually, because for you, our listeners who maybe weren't training models back in 2017, it is really hard to describe just how bad things were. We talk about this pre-progressive era. What was the vibe like in the research labs back then?
Frustrating. I think that's the only word for it.
Yeah.
Because in 2017, if you were working with GANs, you were almost certainly using a DCGAN architecture. Deep convolutional GAN.
And you were just sweating over hyperparameter tuning all day.
Well, constantly. You'd change the learning rate by a fraction, the whole thing would blow up. And if you were lucky, very lucky, you might get a 32 by 32 pixel image of a dog. But half the time, that dog would have two heads, or it would just be a brown smudge.
And mode collapse was the absolute boogeyman.
Constant mode collapse. You'd run a model for days and the generator would just find one single image that fooled the discriminator.
And then it just produces that exact same image over and over again.
Exactly. It just spams the discriminator with that one successful image. But the real aha moment of this paper was the transition in scale. Going from those 32 pixel smears to a 1024 pixel portraits where you could literally see individual strands of hair.
You could see skin pores, the texture of a leather jacket.
It was a quantum leap. It really was.
So here is our roadmap for this deep dive. We are going to completely unpack the training stability problems of 2017, just to understand why this was so hard in the first place.
Because without that context, the solution doesn't seem as magical.
Right. Then we will get into the core methodology, which is the specific growing technique. But we definitely can't stop there. We have to talk about the bag of tricks.
Yes, the bag of tricks.
Things like mini-batch standard deviation and equalized learning rate. Because frankly, the growing part wouldn't have worked without them.
Correct. Those engineering details are so often overlooked in summaries, but they're the unsung heroes here. They are crucial.
We will also discuss how they built the CelebA-HQ dataset, which went on to become a standard benchmark for years. And finally, we will wrap up with our Novel Notions segment, where we pitch some completely wild ideas inspired by this architecture.
I actually have a few interesting ones brewing for that.
I can't wait. Okay, let's unpack this. Let's go back to late 2017, the GAN landscape. What exactly was the state of the art, and why were researchers just banging their heads against the wall?
So in late 2017, the landscape was completely dominated by DCGAN. We were also just starting to see the emergence of Wasserstein-ANs, or WGANs.
Right, which helped with convergence quite a bit.
They did, by changing the loss function to approximate the Earth mover's distance.
Yeah.
But there was this core conflict in generative modeling at the time. You essentially had three main camps.
The tribes of AI.
Exactly. You had the autoregressive models like Pixel CNN. Now, these produced very sharp images, but they were excruciatingly slow to evaluate.
Because they generated pixels one by one sequentially, right?
Yes. pixel by pixel, just completely unscalable for real-time applications or high resolution.
Nobody wants to wait 10 minutes for one image.
Right. Then you had your variational autoencoders, VAEs.
Yeah.
These were fast. They were theoretically grounded, easy to train, but the results were just
super blurry.
Incredibly blurry. Because they optimize for a pixel-wise error, usually means squared error, and that inherently tends to average out high-frequency detail.
So you get what I always call the Vaseline lens effect. Everything looks soft.
Exactly. And then you have the third tribe, the GANs, sharp images, potentially high resolution, but incredibly, infuriatingly unstable. The biggest hurdle was what we call the gradient problem when you try to scale up.
Let's break that down for the listener. Why does high resolution break the gradients? Like, why can't I just take a working DC GAN, add 3 more upsampling layers to make it bigger, and just run it?
Think about the discriminator's job. It has to look at an image and say real or fake. If you were trying to generate a 1024 by 1024 image from scratch, and your network is initialized with random weights, the output is just noise.
Just complete high-frequency garbage.
Yes. The discriminator looks at a real high-res photo from your dataset, which has beautiful structure, lighting, texture, and then it looks at this pile of random noise. It is trivially easy to tell them apart.
It's like asking a master art critic to judge a toddler's finger painting against a Rembrandt.
That's a great analogy.
The critic doesn't even need to think about it. It's instantly obvious.
Precisely. And because it is so easy, the discriminator wins instantly. In a GAN, the generator learns from the gradient of the discriminator's decision boundary.
It relies on that feedback to get better.
Right. But if the discriminator is 100% confident and practically perfect right out of the gate, the gradient it sends back to the generator is completely useless.
It's either zero or random noise.
Yes. It essentially says, I have nothing to teach you because you are so far off. There is no useful learning signal. The generator literally doesn't know how to improve because the gap between its output and reality is just too wide.
And there is a massive memory constraint at play here too.
Huge constraint. Remember, this is 2017. A 1024 by 1024 image takes up a massive amount of VRAM on a GPU, especially when you are calculating all those gradients for backpropagation.
So you can't run a batch size of 128 or 256.
Not even close. You have to use incredibly small mini batches, maybe only 4 or 8 images per batch.
And small batches mean incredibly noisy gradients.
Extremely noisy gradients.
Yeah.
So you have unstable training, the model diverges and it collapses. You're trapped in this catch-22. You need high resolution for the images to look good, but high resolution makes the discriminator too strong and the batches too small, which makes training impossible.
Enter Nvidia with the progressive growing concept. Let's look at this core methodology because it's so elegant. They paper proposes a curriculum. Instead of trying to paint the Rembrandt immediately, they say, let's start with the toddler sketch.
Right. They start with a generator and a discriminator that are tiny, just 4 pixels by 4 pixels.
4 by 4. That is effectively just a couple of broad colors.
It is. It's learning the average color of the data set and maybe a very, very vague sense of geometry. Like, is there a dark blob in the middle? But because it is only 4 by 4, the training is incredibly stable. The manifold of real images downsampled to 4 by 4 is simple. The discriminator can't overpower the generator because there just isn't that much detail to scrutinize.
And the memory footprint for a 4 by 4 image is basically negligible. You can use huge batch sizes.
Exactly. So they train this 4 by 4 network until it stabilizes. Then they double it. They add layers to the generator and the discriminator simultaneously to handle 8 by 8.
And then they train that.
Right, then they double it again to 16 by 16, then 32, 64, all the way up to 1024.
But wait, this is where I have to play the skeptic, or at least the devil's advocate for the listener. If I have a trained neural network...
A complex system.
Yeah, a complex system where the weights are finely tuned to produce a 4 by 4 output, and I just slap brand new randomly initialized layers on top of it, doesn't that just break the network? You are changing the architecture mid-flight. That usually causes what researchers call catastrophic forgetting. It's a total shock to the system.
You are spot on. If you just initialized new layers with random weights and wire them directly in, the sudden injection of huge random noise into the forward pass would instantly destroy all the learned features of the previous layers.
The gradients would explode.
They would explode and the network would instantly forget everything it learned at the 4 by 4 stage.
So how do they actually avoid the shock? What's the trick?
The crucial detail here is the fading in technique. You cannot simply slap the new layers on. You have to fade them in smoothly over time.
Walk us through the visualization of this. How do you fade in a layer in a computational graph? It's not an audio mixer.
Well, it kind of is, actually. Imagine you are at the 16 by 16 resolution stage.
Yep.
Your network is stable. Now you want to go to 32 by 32. You don't just switch the output layer out. You create a new branch.
Okay, a break.
You take your 16 by 16 feature map from the generator, and you use a simple nearest neighbor upsampling operation to just stretch it to 32 by 32. That becomes your old path.
So it's blurry, it's blocky.
Yes, but it carries all the existing knowledge safely. It's stable.
Right. No new information, just bigger pixels.
Exactly. But in parallel to that, you have your new branch. These are your new convolutional layers that are actually learning to output fine 32 by 32 details. You combine these two parallel paths using a parameter they call alpha.
And alpha acts like a weighted sum between the two branches.
Exactly like an audio mixer. The formula is essentially the final output equals 1 minus alpha times the old path plus alpha times the new path.
Okay, that makes sense.
At the very start of the resolution transition, alpha is set to exactly 0. So the network is effectively completely ignoring the new layers and just using the simple upsampled old stuff.
It behaves exactly as it did before the transition.
Yes. So the gradient flow through the new layers is minimal or non-existent initially. They don't disrupt anything. Then over the course of thousands and thousands of iterations, they linearly increase that alpha value from 0 up to 1.
So as alpha slowly grows, the new layers start contributing just a faint signal to the output.
Right. The network slowly adjusts to this new, tiny signal without ever losing the stability of the base features.
Slowly, the new layers start contributing more and more to the final image. And by the time alpha hits 1, the new layers are fully in charge.
Yes. And at that point, you can just discard the simple upsampling branch entirely. You're fully at the new resolution.
That avoids the shock perfectly. The network retains its pre-existing knowledge of the large-scale structure,
The phase shape, the background.
while slowly integrating the new higher frequency details, like the edge definition or the lighting.
Exactly.
You know, it really mimics biological development in a way. Infants don't see with 20/20 vision immediately when they are born.
Right. Their vision starts blurry.
It starts incredibly blurry and then sharpens over months. And neurologically, this prevents their brains from being totally overwhelmed by sensory input before they even understand basic concepts like object permanence.
It really does mirror that.
Yeah.
And the result in the GAN is that the network learns the broad strokes first. It learns here's a head, here's a background at 4x4.
Then, here are eyes and a mouth at maybe 32 by 32.
And then here are individual eyelashes at 1024. It never has to learn everything all at once. It builds a foundation.
And I imagine this had a massive impact on training speed too, didn't it?
It was a massive speed up because you spend a lot of your training iterations at 4x4, 8x8, and 16 by 16.
Where compute is dirt cheap.
Cheap compute,
Yeah.
low VRAM usage. The model learns 2 to 6 times faster overall than if you tried to train a high-res model from the start. You are doing all the heavy lifting of global structure when the barbell is incredibly light.
That is just brilliant engineering. So that is the headline. Progressive growing. Starting small, fading in layers. But the authors are very clear in the paper that progressive growing alone actually wasn't enough.
No, it wasn't.
If you just did the fading trick, you would still run into massive issues at the higher resolutions. They needed a bag of tricks to solve the remaining stability and variation issues.
Yes. And honestly, if you're a practitioner or an engineer listening to this, these tricks are arguably just as valuable as the progressive concept itself. These are the absolute nuts and bolts of how you actually make a GAN converge.
Let's talk about problem number 1 in that bag. Variation.
Right. Mode collapse.
We mentioned it earlier. The generator finds one really good face and just spams it. How did they actually solve this?
They introduced something called mini-batch standard deviation.
Okay, let's break down the mechanism of that. Because why does a normal discriminator fail to stop mode collapse in the first place?
Think about how a standard discriminator processes data. It looks at images one by one. It essentially asks a single question. Does this individual image look like a real photograph?
It has no concept of the group or the batch.
Exactly. It's completely blind to the context. So if I showed the discriminator a batch of 16 identical generated dogs, it just looks at the first one and says, yes, that is a realistic dog. Then looks at the second one and says, yes, realistic dog.
It doesn't realize that a real data set wouldn't have 16 identical dogs in a row.
Right. It doesn't realize that a batch should have natural variety.
So the researchers needed a way to force the discriminator to look at the statistics of the batch as a whole, not just the pixels of the individual image.
Yes. And here's the exact recipe they used. You take a mini batch of feature maps inside the discriminator. Usually this is done towards the very end of the network, where the features are highly semantic.
Okay.
You compute the standard deviation of these features across the batch dimension.
Let me make sure I have this right. So for every single pixel location or spatial location in that feature map, you check how much the numerical values vary across the, say, 16 different images in that specific batch.
Correct. If the images are all identical,
Which means mode collapses happen.
then the standard deviation across the batch is exactly 0. There is no variance. But if the images are all different, representing a healthy, diverse batch, the standard deviation is high.
So they calculate the standard deviation map.
And then they average it into a single scalar value, just one single number that represents the global diversity score of that entire batch.
Just one number.
Just one number. Then they replicate that single value to match the spatial dimensions of the feature map, and they just append it as an extra feature map.
Basically just concatenating an extra color channel to the discriminator's internal representation.
Exactly. It's incredibly elegant.
That is surprisingly simple. It is essentially giving the discriminator a cheat sheet that says, hey, just so you know, the variation in this batch you're looking at is 0.
That's exactly what it is. And because the discriminator's entire goal is to distinguish real data from fake data, and real data naturally has high variation, it quickly learns to rely on that extra feature map.
If the variation score is too low, it immediately knows it's looking at a fake collapsed batch.
Right, and it harshly penalizes the generator.
So it forces the generator to produce variety just to survive the discriminator's critique.
Precisely. It doesn't require a massively complex new loss function. It just requires giving the discriminator access to the right statistical information.
I love that. Pure, simple engineering. Now, let's talk about the second big problem they tackled. Unhealthy competition, or what some call the arms race.
This is all about signal magnitudes inside the network.
All right. As the generator and discriminator fight each other back and forth, the signal magnitudes, the actual numerical values of the weights and activations inside the network, they tend to spiral out of control.
They get larger and larger as each network tries to overpower the other,
leading to exploding gradients and total network failure.
which creates massive instability. So the paper introduces 2 distinct solutions for this. The first one is equalized learning rate.
Now, this is fascinating because it departs from the standard weight initialization techniques we all learned in school, like Xavier initialization or He initialization.
It does.
Usually, you initialize your weights very carefully based on the layer size so that the variance of the activation stays relatively consistent throughout the depth of the network.
That's the traditional wisdom, yes.
Yeah.
But Karras and the team argue that those initialization methods are entirely static.
Meaning they only happen once.
Right, you set the weights carefully once at the very beginning of training. But optimization is a dynamic process. The weights change. So Karras said, no, let's throw that out. Let's just initialize everything trivially with a standard normal distribution, 0 mean, unit variance.
Just a basic N01 distribution that seems almost careless for such a complex model.
It sounds careless on the surface, but here's the trick. They scale the weights dynamically at runtime. Every single time the forward pass happens, they multiply the weights by a scaling factor.
Jen, what's the factor?
It's based on the layer's dimension. Specifically, it's the square root of 2 over the number of input connections to that layer.
But wait, why do it at runtime instead of just initializing it that way once? Mathematically, isn't a wait times a constant exactly the same whether you set it early or calculate it later?
Mathematically, the forward pass is identical, but it relates entirely to the optimizer. Specifically, modern adaptive optimizers like Atom or RMS Prop.
Ah, okay. How so?
These optimizers normalize their gradient updates based on an estimated standard deviation of past gradients. They are adaptive.
Right. Atom tries to guess the optimal learning rate for each individual parameter.
Exactly. But if you have some parameters in your network that have a huge dynamic range and some that are tiny, the optimizer really struggles to find a base learning rate that works for both extremes simultaneously.
Because Atom is trying to normalize things that are on completely different scales.
Yes. So by normalizing the weights dynamically during the forward pass, they ensure that the actual parameters the optimizer sees and updates are all strictly in that standard normal range.
Wow. So all weights, regardless of the dynamic range of their specific layer, effectively learn at the exact same speed.
Exactly. It levels the playing field for every single parameter in the network. It prevents one massive layer from dominating the learning process just because it happens to have more connections.
It ensures the learning rate is actually literally equalized across the entire depth of the architecture.
It is a really deep engineering insight. It's not just fixing the architecture, it's fixing the interaction between the architecture and the atom optimizer.
It really is. And the second solution they had for this signal escalation problem was pixel-wise feature vector normalization.
That is quite a mouthful.
It is. What does it actually do in practice?
It is actually a very heavy-handed constraint on the network. After every single convolutional layer in the generator, they look at the feature vector at each pixel location.
Okay, so imagine you have a layer with 512 channels.
Right, so that is a 512-dimensional vector sitting at one single pixel coordinate.
Got it.
They normalize that entire 512-dimensional vector to unit length. They literally divide it by its own magnitude.
They just force the math to stay within a unit hypersphere. That seems incredibly destructive. Wouldn't that destroy valuable information in the magnitude of those activations?
You would absolutely think so. It goes against the intuition of letting neural networks represent intensity. But they found empirically that in these specific generative visual tasks, the magnitude of the signal doesn't actually matter as much for the visual content.
So what matters?
The direction of the vector in that high-dimensional space.
So the semantic information, whether this pixel is part of an eye or part of the background, is encoded in the relative values of the channels to each other, not the absolute volume of the activation.
Exactly. So by normalizing the magnitude, they put a hard cap on the signal exploding. It keeps everything strictly bounded without actually destroying the geometric structure of the image being generated.
It acts almost like a hard limiter on a stereo system.
That's a great way to put it. It prevents the signal from clipping and distorting without fundamentally changing the melody of the song.
Okay, so to recap this amazing engineering effort, we have the progressive growing curriculum to handle the fundamental gradient problem.
Right.
We have the mini-batch standard deviation to force variety and kill mode collapse.
Yep.
And we have equalized learning rate and pixel-wise normalization to keep the underlying math completely stable during the arms race.
A very robust foundation.
But now, they needed data. You can't train a revolutionary high-res model on garbage data.
And this is a part of the paper that so often gets glossed over in summaries. But it was a massive, massive engineering effort on its own. They quickly realized that existing data sets at the time, things like CFAR, Elysium, even the standard CelebA dataset, were essentially trash for what they wanted to achieve.
They were just too low res, or they were completely full of JPEG compression artifacts.
Right. You absolutely cannot train a pristine 1024 by 1024 generator on 256 by 256 heavily compressed JPEGs.
Because if you do, the generator doesn't learn what a face looks like. It just learns to perfectly generate JPEG artifacts.
It learns the noise. Exactly.
So they had to create CelebA-HQ.
They did. High quality.
Walk us through this process because it's nuts. They started with the original CelebA in the wild images, right?
Yes, which were just standard JPEGs downloaded from the internet with wildly varied quality. Step 1, they actually trained a completely separate neural network whose only job was to remove JPEG artifacts from these images.
That is dedication. They used an AI to clean the training data for the main AI.
It was necessary. Then step 2, they used yet another adversarial network for 4x super resolution. They needed to intelligently upscale these cleaned images.
Because you can't just stretch them, they needed to hallucinate the missing high frequency details to get to a higher base resolution realistically.
Right. Then step 3, which is crucial, alignment.
They used facial landmark detection for this.
Yes, they used an algorithm to find the exact coordinates of the eyes and the mouth in every single image. Then they performed a highly precise mathematical alignment and cropping. If you look at the final CelebA-HQ dataset, the eyes of the person are always in the exact same pixel coordinates across all 30,000 images.
Why is that rigid alignment so incredibly important for training a GAN?
Because it drastically simplifies the problem space for the generator. If the eyes are randomly moving around the image, the generator has to dedicate a huge amount of its limited parameter capacity just learning where to put the eyes on the canvas.
Right.
But if they are fixed at, say, pixel 400, 500, the generator doesn't waste any capacity on position.
Right.
You can focus 100% of its capacity on learning exactly what an eye looks like.
The texture, the iris, the reflections, the eyelashes.
Exactly. It frees up the network to focus on quality rather than layout.
They even went so far as to use mirror padding and Gaussian filtering, didn't they?
Yes, on the edges of the images. This is to create a sort of artificial depth of field effect. They intentionally blurred the background behind the aligned faces.
Why blur it? Wouldn't you want sharp backgrounds?
Not necessarily. Again, this was a conscious choice to stop the generator from wasting precious resources trying to model incredibly complex, high-frequency, sharp background noise like trees or brick walls. They wanted it to focus all its power on the face itself.
And finally, after all that processing, they didn't just take all 200,000 images.
No, they algorithmically selected only the best 30,000 images based on frequency-based quality metrics. They just ruthlessly threw out anything that was still blurry or poorly aligned,
resulting in a dataset that was absolutely pristine, sharp, high-res, perfectly aligned.
And CelebA-HQ instantly became the gold standard for generative benchmark testing for years to come.
It really shifted the whole field. Before this paper, researchers were perfectly happy generating these blurry, low-res bedroom scenes. After this paper dropped, if you weren't generating 1024 by 1024 photorealistic faces, you simply weren't competitive anymore.
It single-handedly raised the bar for data hygiene and output expectations in generative AI.
Let's talk about the results. They put this whole system, the progressive growing, the bag of tricks, the pristine CelebA-HQ data to the test. What did they actually see when it finished training?
Visually, it was shocking. I distinctly remember seeing these images for the first time online. The 1024 by 1024 celebrity faces had razor-sharp hair.
And hair is notoriously difficult for neural networks.
Incredibly difficult, because random high-frequency noise looks a lot like hair to a computer, but real hair has flow. It has physical structure and lighting. This model actually captured that flow.
And the skin textures.
Hyper-realistic.
Yeah.
Pores, fine wrinkles, subtle imperfections, freckles. It did not look like smooth plastic, which was the absolute hallmark of VAEs and the earlier GANs.
They also tested the architecture on LSUN categories, right? Like bedrooms, churches, cats.
They did. And the results there were reasonable. But they actually revealed some of the inherent limitations of the architecture. The images were very high resolution, but if you looked closely, you started to see the logical consistency break down.
What do you mean by logical consistency?
Well, a bedroom image might look incredibly sharp, but it might have a bed that just weirdly melts into the wall. Or a generated church might have a beautiful stone spire, but the spire curves like a banana.
So the texture quality was perfect. The stone looked exactly like stone. The fabric on the bed looked like fabric.
But the underlying geometry was often totally nonsensical.
It really highlights the fact that the model doesn't actually understand objects in a 3D space, right? It only understands 2D textures and local statistical patterns.
Exactly. It's essentially a brilliant texture synthesis engine that's memorized the statistical correlation of shapes, but it has zero conceptual understanding of how the 3D world operates.
Still, on the metrics, they completely dominated. They achieved a record inception score on the unsupervised CIFAR-10 benchmark.
Yes, a score of 8.80, which was massive because the previous state-of-the-art was only around 7.86.
But interestingly, the authors were quite critical of the existing metrics themselves. They felt that MSSM multi-scale structural similarity was really failing the community. Why was that?
MSSM essentially measures output variation. It tells you if your generated images are sufficiently different from each other.
Okay, that sounds like a good way to test for mode collapse.
It sounds good, but here's the fatal flaw. A mode collapse generator that produces, say, 5 totally different but absolute garbage images could actually score very well on MSSM.
Really?
Yes. Or a generator that completely overfits and just memorizes the training set could score perfectly. It measures internal variation, but it doesn't robustly measure the quality of that variation relative to the true training distribution.
So they proposed a brand new metric, sliced Wasserstein distance, or SWD.
Right. This is a bit mathematically dense, but it's fundamentally important for validating their specific progressive claim. What they do is they extract thousands of local patches from the images at multiple different scales using a Laplacian pyramid.
A Laplacian pyramid basically breaks the image down into distinct frequency bands, right? From low frequency, which is broad shapes, to high frequency, which is tiny pixel details.
Correct. So they extract patches from the 16 by 16 level, representing large structure, and patches all the way up to the 1024 by 1024 level, representing pixel level details. And then they compare the statistical distribution of these extracted patches in the generated images against the patches extracted from the real training images, using the Wasserstein distance, also known as the Earth Mover's distance.
So they are essentially checking two things independently. Do my generated high-frequency texture patches statistically match real texture patches? And do my generated low-frequency shape patches match real shape patches?
Exactly. It beautifully separates large-scale global structure from pixel-level local attributes.
Right.
And their SWD metrics showed quantitatively that progressive growing improved quality at every single scale.
It proved mathematically that the curriculum training wasn't just helping the fine details, it was actively helping the global structure too.
Yes, it validated the entire premise of the paper.
Now, before we move on to the legacy of this paper, we really have to address the ghosts.
Ah, yes, the ghosts.
In the unsupervised CFAR-10 training section, they noticed something incredibly creepy in the latent space interpolations.
Yes. So when you train a GAN on CFAR-10, without any labels, meaning the model has no idea that this is a car or this is a horse, it has to learn everything in one massive continuous latent space. It has to learn the transitions between completely unrelated classes.
Because the latent space is just a continuous vector space. There are no hard boundaries.
Right. So logically, somewhere in that high-dimensional math, there exists a point that is exactly halfway between a generated car and a generated horse.
A car-horse hybrid.
A ghost. A nightmarish morphing fusion of metal and flesh.
Wow.
The paper explicitly notes that maximizing the inception score often naturally minimizes the appearance of these ghosts, but they are an inevitable artifact of unsupervised training in a continuous space.
It's fascinating because it implies the model isn't just a database switching between memorized templates. It is actively mathematically trying to morph the features.
It is trying to find a smooth, continuous manifold that somehow logically connects a glass windshield to a leather saddle.
It fails visually, of course, but the attempt is mathematically fascinating. Let's move to the legacy and the limitations. This paper was an absolute triumph, but it wasn't perfect. What were the specific limitations the authors themselves admitted to?
Well, we touched on it briefly. Semantic sensibility. The model is a master of texture, but a complete novice at geometry. It doesn't understand objects. It creates textures that merely look like objects.
So you might get a perfectly generated face, but one earring is completely different from the other earring.
Yes, because it doesn't know what an earring is, or that they usually come in matching pairs.
Or a collared shirt that just sort of merges seamlessly into the skin of the neck.
Exactly. It severely lacks structural 3D understanding. It also still struggled with microstructure if you zoomed all the way in. It wasn't perfectly photorealistic if you really started pixel peeping.
But historically speaking, its impact was massive.
Historically, it is the bridge. It conclusively proved that curriculum learning starting easy and progressively getting harder applies incredibly effectively to deep generative models.
It paved the way directly for StyleA-GAN, didn't it?
Yes. StyleA-GAN was published by Karras and Nvidia a bit later. StyleA-GAN fixed a lot of those structural semantic issues by fundamentally changing how the latent code is injected into the network.
But StyleA-GAN kept the progressive growing spirit entirely alive in its early versions.
It absolutely did. Progressive growing moved GANs out of the theoretical lab. Suddenly, real artists could use this tech.
Yeah.
Game designers could use it. It was really the first time AI image generation felt usable.
It was the specific moment generative AI went from being a quirky academic curiosity to a legitimate creative tool.
I completely agree.
So what does this all mean for us today, sitting here in 2026?
I think it reminds us that very often the solution to a bottleneck isn't just throwing a bigger, deeper neural network at the problem. It's designing a smarter training process.
Right.
They solved an impossible optimization problem, not by adding billions of parameters, but by fundamentally changing how those parameters were exposed to data over time.
That is a deeply powerful takeaway. Okay, are you ready?
I am ready. Let's hear it.
It is time for novel notions.
Let's do it.
Quick reminder to you, our listeners, this segment is for entertainment purposes only. These are entirely unproven, outlandish, half-baked research pitches inspired by the legacy of today's paper. Do not try this at home, or do, and just make sure you cite us when you win your Turing Award.
What is your pitch today?
I am calling this one the soft brain transplant.
Okay, you definitely have my attention with that name.
Here is the core problem. Transfer learning today is essentially violent.
Violent, how so?
You take a massive model that is fully trained on, say, legal documents. It's an expert in law. Now you want to teach it medicine. Usually we either freeze a bunch of weights or we just fine-tune the whole thing with a very low learning rate.
Right.
But this almost always causes catastrophic forgetting. The model literally overwrites its legal pathways to learn the medical pathways. It forgets law to learn medicine.
It's a zero-sum game for the parameter weights.
Exactly. So I want to use the alpha fading logic from the progressive GAN paper to fix this.
Oh, I see where you're going.
Imagine a progressive domain growing architecture. You have your law block, a massive, fully trained transformer block. You don't touch it. Instead, you instantiate a brand new, distinct medicine block completely parallel to it.
Okay, so you are physically adding capacity to the network, not just overwriting the old capacity.
Exactly. But just like the paper, you don't just wire it in and switch it on. That would break the outputs. You use a smooth alpha transition parameter to fade the influence of the new medicine block into the final decision-making process over thousands of training steps.
Fading in a new domain.
But here's a real kicker. During this fade-in, you strictly monitor the mini-batch standard deviation of the final activations.
Wait, to ensure variation, like in the GAN?
Not exactly. To ensure the model doesn't mathematically collapse into only knowing medicine, you force the statistical distribution of the activations to remain consistent with the original law distribution while slowly injecting the new medicine signals.
Wow, a soft transplant.
Right. The brain never goes into shock. It just slowly learns to incorporate a new lobe.
That is genuinely interesting. You are essentially growing a new lobe of the brain and slowly chemically wiring it up rather than violently overwriting the existing neurons. You could theoretically end up with a multi-lobed expert model where those alpha parameters act as a dynamic attention mechanism at inference time.
Exactly. You want legal advice, alpha is 0. You want medical advice, alpha is 1. No more catastrophic forgetting, just the progressive growing of expertise.
I actually really like it. It's like a mixture of experts architecture, but grown organically and continuously rather than being hard-routed.
Okay, what is your pitch?
I call mine the blurry world hypothesis for reinforcement learning.
The blurry world hypothesis. Go on.
RL agents generally suck in complex visual environments. They are incredibly brittle. And I think it's because the simulated world we put them in is just too high res right from the start.
Yeah, give them too much detail.
Yes.
Yeah.
We drop a newly initialized self-driving car agent into a hyper-realistic simulator with 4K textures, real-time ray tracing, dynamic shadows, complex reflections, and we just say drive.
And it immediately crashes.
Because it gets completely overwhelmed by the raw pixel space. It's trying to interpret the high-frequency texture of the oak leaves on the trees before it has even learned the basic concept of staying on the asphalt.
It wastes millions of gradient updates trying to parse irrelevant background noise.
Exactly. So my pitch is progressive resolution reinforcement learning. We apply the exact 4x4 up to 124 curriculum from the GAN paper directly to the RL agent's perception of its environment.
Oh, that's brilliant. So in phase 1.
In phase 1, the agent is dropped into the 4K simulator, but its camera feed is heavily downsampled. It only sees a 4x4 pixel grid of the world. It is practically blind.
It just sees vague patches of light and dark.
Exactly. And at that resolution, it learns basic survival. It learns the simplest policy, don't drive into the big dark blob. Because the dark blob is a wall.
It stabilizes the fundamental survival instinct first.
Right. Then, once that policy is stable, we slowly fade in the 8x8 resolution. Suddenly, it sees a slightly more defined environment. It learns, okay, stay on the long gray strip. That's the road.
Then we fade in 16 by 16.
Yes, and it learns about curbs. And only at the very end, at 1024 by 1024, does it finally have enough resolution to start learning to read complex traffic signs.
But by the time it's finally analyzing a stop sign, the underlying policy for steering the car and staying on the road is already frozen and robust.
Exactly. We would use the equalized learning rate trick from the paper to ensure the policy network's weights don't explode every time the sensory input dimension doubles. It perfectly mimics biological development.
Right. Infants don't need to read road signs. They just need to learn not to fall over when they walk.
Exactly. We shelter biological brains from high-frequency detail until their core motor functions are stable. We should do the same for RL agents.
You know, that leads me to a really provocative thought to end on. If we know that neural networks learn best by starting with a blurry, low-res view of the world, maybe we are feeding our modern large language models and text agents high-fidelity data way too quickly.
Oh, that's a profound thought.
Are we stunting their deeper reasoning by throwing the entire internet at them on Epoch 1? Maybe we need a progressive growing of text. Start by training an LLM entirely on simple subject-verb-object grammar. just basic structural logic.
Right. And only once it understands basic logic, you slowly fade in complex subordinate clauses.
And then fade in sarcasm, and then poetry.
The kindergarten approach to artificial general intelligence.
Precisely. Build the foundation first.
I love it.
Well, that brings us to the end of another deep dive. To recap today's journey, starting small is unequivocally the key to getting big results. And never, ever underestimate the power of the boring stuff.
Never.
Simple normalization and standard deviation tricks are truly the unsung heroes of the entire AI revolution.
They really are. If you are a practitioner listening to this, don't just read the abstract of these classic papers. Read the appendix. The actual magic that makes it work is almost always hidden in the math in the appendix.
The link to the paper Progressive Growing of GANs is in the description. Read it. It is an absolute masterclass in engineering stability out of chaos.
And keep an eye out for those ghosts in the latent space.
This has been Talk Tensors. Calibrate your weights, and we will see you in the future.